Hello, everyone, and welcome to lecture series DEM and CFD-DEM with PhasicFlow. This is the second lecture, and in this lecture, we are going to talk about the basics of the DEM and perform a bit more complex DEM simulation. I am Hamid Reza Nourouzi with my friend and colleague Bahram. Bahram, please. And you may want to explain a little bit about the last session and the topics that we covered in the last section.
Yeah, thank you very much. Also, hello from my side. Welcome back. So I hope that you enjoyed the last session and you're going to learn more from this session. Last session, basically, Hamid tried to introduce you to the basics of DEM, what is DEM, and of course, a bit about the PhasicFlow. What is PhasicFlow? So as an open source tool for doing DEM simulations. And he also tried to do together with you a case setup, a very simple case setup using the PhasicFlow that was a rotating drum. So we did that simulation, and we also had the first look at the results. In the today's session, as Hamid already mentioned, we are going to continue with that, going a bit more into the details of settings in the PhasicFlow, with, of course, explaining about their connection to the DEM properties or the particle properties, and doing a bit more complex simulation. So I will be today with Hamid to support him. If there are any questions, please feel free to put them in the chat. I try to answer them as far as possible by myself through the chat, or I will bring them up to Hamid. So your contributions, your questions are very highly welcome. So because that somehow encourage us, that also gives us feedback that you are with us, you're listening, and if there is something unclear, then we try to clarify it. And for those of you who might have missed the previous lecture, so it's available on Hamid's YouTube. Please feel free to watch it, and also if there are also questions about those lectures, you can ask them in these or next sessions. So Hamid, please.
Okay, thank you, Bahram, for your nice summary. As I told you, I want to talk about the basics of the DEM and why we choose some parameters in DEM and why we, for example, choose very small time step. We set the simulation domain and everything about the DEM and the background of the DEM. All the materials that are presented in this lecture is from this book, Coupled CFD-DEM Modeling, Formulation, Implementation, and Application to Multi-Phase Flow. If I miss some parts and you don't understand some parts, you can get this book and read chapter 2 and chapter 3. All the materials are from chapter 2 and chapter 3 of this book. In DEM, we have two main approaches, hard sphere and soft sphere. In the hard sphere approach, we have particles pairwise contact between the particles. The contacts are instantaneous, and we do not allow particles to have overlap. This means that we only can have a pairwise contact between particles. Pairwise contact is something that we see in the dilute system. So the hard sphere approach is the approach that is used for dilute systems. In contrast, the soft sphere approach, in the soft sphere approach, we allow particles to have slight overlap with each other. And each contact between two particles lasts for a period of time, for multiple time steps. And in this context, we can have a particle with multiple contacts with the surrounding particles. So we can assume that at this condition, that this approach can be applied to both dilute and dense systems. So it has a wider application compared to the hard sphere approach. And of course, in the context of the soft sphere approach, we can easily add the long-range forces and other interactions between the particles in the formulation. So comparing these two approaches and considering the fact that we are going to have a more general software that is applicable to a wider range of applications, soft sphere is the choice for DEM simulations instead of hard sphere. Based on the soft sphere, we track each particle in the system. We have two equations for each particle. One equation is for translational motion. It is a well-known equation, the well-known equation, Newton's second law of motion. And the second equation is the Euler's equation, which is used for defining the rotational motion of the particle. Of course, these two equations are used for spherical particles. For non-spherical particles, the second equation, Euler's equation, is a bit different. And of course, as I told you, two particles that are in contact are allowed to have a slight overlap. And based on this overlap that you see in this picture, we calculate the contact force and mechanical contact force between the particles. So as you see here, the first equation has some terms in it. The first term is the particle-particle contact force. The second term is the fluid-particle contact force. This term appears when we have fluid-particle interaction, like like gas-solid flows, like liquid-solid flows, like those that we see in the spotted bed simulation or in the fluidized bed simulation. And the last term is the gravitational force. And in the second equation, the first term is the tangential torque, and the second term is the rolling friction torque, and the second term is responsible for dissipating the rotation of the particle, and this term prevent particle from a continuous and infinite rotation over time. As I told you, we calculate the contact force between the particles based on the partial overlap that those particles have. We have different closure laws or models for calculating the contact force. In PhasicFlow, we have two sets of the contact force models, linear and nonlinear. Of course, if you search the open literature or you read the book that I referenced at the beginning of this session, you will find a wider range of the contact forces. For the linear contact force, we use a spring and a dashpot for defining the normal and tangential contact force. For the normal contact force, as you see, the contact force is composed of two terms, elastic and dissipative. The elastic term is responsible for conserving the kinetic energy, and the dissipative term is responsible for dissipating. So if I want to, for example, have a particle that dissipates more energy, I need to somehow increase the value of the dissipation contact force or dissipation term. In the tangential direction, we use the same equation again, the elastic term and the dissipative term. And as you see here, there are some variables or parameters in these equations that have underlined. These properties are those properties that we are required to provide to the software to so that the code or the software can calculate the contact force between the particles. For example, the first one is Kn, is the spring stiffness in the normal direction. The second one is the spring stiffness in the tangential direction. This is the damping coefficient, which is related to the restitution coefficient in the normal direction again. And this is the parameter that we should supply to the, or we should provide to the code. And also for the friction, we also have the Coulomb's friction law here. This equation also requires us to provide the dynamic friction. And again, for the normal, for the rolling friction, we need to provide the rolling coefficient here. So as you see here, 1, 2, 3, 4, 5, and of course, restitution coefficient in the tangential direction. 6 parameters should be defined for particles as the physical properties to use a linear contact force model in the code.
Hamid, maybe a question regarding the hard sphere. Do you know any code, any code out there uses a hard sphere, or all the codes are using the soft sphere? And if they are using it for in what case?
I'm not aware of any code that uses hard sphere, but I assume that those codes that use a kind of particle tracking method use hard sphere for at least calculation of the contact between the particle and the valve. But all of the available DEM source codes and commercial softwares use soft sphere.
Okay, so basically it might be useful in the Lagrangian tracking.
Yes.
And maybe I also wanted to add something to this slide, to this linear contact force. As Hamid mentioned, there are 6 parameters that are sort of quite important for setting up a physically correct DEM simulations. And it's also quite well known in the field that finding these parameters is a big challenge. So for those of you who are already familiar with fluid dynamics and CFD, for example, viscosity is a material property that we need that we can somehow describe the flow behavior or the fluid behavior. And these are similar properties that we need for the particles to describe the particle behavior when it comes in touch with the other particles and with the walls. But unlike the CFD side, on the CFD, when we talk about viscosity, there are very well-known methods for measuring the viscosity, and it's not usually that complicated to measure viscosity. Of course, we have also complicated cases, but in most of the cases, we can easily measure it. But in here, measuring these parameters can be a very, very big challenge. So therefore, and that's why, therefore, calibration and validation in the DEM also plays a very, very important role. And there are also some standardized case for calibrating and validating these parameters. For example, this rotating drum that we already simulated last time, although it's a very, very simple simulation, but it's one of the often used cases for calibration and validation of these parameters. So Hamid, please.
Yeah, thank you for your nice explanation. Of course, you're right. Calibration and adjusting the parameters that are hard to measure via experimental methods is a very vital and important part of any DEM simulation. Beside the linear contact force model, we have nonlinear model. It is somehow similar to the linear model, spring dashpot. For the normal direction, we have again elastic term and dissipative term, and you see we need to provide the Young modulus and shear modulus for the as the material properties to the software. And again, the damping coefficient is also related to the normal restitution and the tangential restitution coefficient. Again, the same friction law is used for the nonlinear model, the friction, Coulomb's friction law, and rolling friction model that we use in the PhasicFlow. These are the 2 main approaches or 2 main contact force models in the DEM. Of course, you will find a variation and alternative approaches for calculating the contact force between the particles. And as I told you, it is fairly straightforward to implement new contact force models in PhasicFlow. Just read the source code and you will understand how you can do that. The main steps in the CFD, in the DEM simulation are presented here. As you see here, there are 8 main steps, at least from my point of view. The first step is the simulation setup. We should provide the particle data like velocity, initial position, the geometry of the container, the properties of the particles and the walls, and all the necessary data that are that the code requires to start the simulation. In each iteration, as you see here, iteration starts from the second step to the last step. In each iteration, we have a set of operations that are called pre-iteration. For example, we may want to insert particles during the simulation into the domain, or we set the contact force and other parameter that should be initialized to 0. We do this operation in the pre-iteration step. And if the integration method is the predictor corrector type, then in the third step, we have the prediction step. And with prediction, I mean that we use the previous velocity and acceleration to predict the next position and velocity of the particle in the simulation. And then after this step, everything is calculated. For example, contact force and acceleration is calculated based on the predicted velocity and position of the particles. And in the fourth step, we have contact search. We find the contact between the particles and find the list of the particles that are in contact. And in the next step, which is the fifth stage, we calculate the contact properties. By contact properties, I mean the contact force, contact torque, and if there are any kind of long-range force, we also can calculate the long-range force between the particles. Having the the torque and the contact torque and contact force between the particles, we can calculate the acceleration of the particles, both translational or linear acceleration and rotational acceleration. And having linear and rotational acceleration, we can integrate the equations of the motions, Newton's second law of motion, Euler's second law of motion, and we can update the velocity and position of the particles out of this integration step. And of course, the last step is the output. If I want to save the results on the file, on the disk, to have it for later post-processing or visualization. And this loop that you see here, that starts from the second step and ends in the last step, continues up to the end of the simulation. So knowing these steps, we can discuss some main parts of the calculations. For example, I want to talk about a little bit about contact search, and I also want to talk about the integration, because I think that these are the very important parts of the DEM simulation, and we should know about them. I want to first talk about the contact search. As I told you in the previous session, we need to define a simulation domain. In PhasicFlow, simulation domain is a cuboid, which is defined by 2 coordinate points, minimum coordinate points and the maximum coordinate points, and all the particles are inside this simulation domain, and everything outside of this simulation domain is invalid and gets deleted. For the contact search, we have, in general, we have 2 main approaches. The first approach is cell-based contact search, and the second approach is a kind of tree-based contact search. The reason that we use a contact search algorithm is that we want to reduce the list of the possible contacts and reduce the number of the collision checks that we perform between the particles. For example, if I'm searching the contacts between the particle 1 and the surrounding particles, I somehow do not need to perform any collision check between particle 1 and particle 8 or 9 or 3 or 7. So I just need to check the particle contact or collision check between the particle 1 and the surrounding particle, the particles that are in close proximity of the target particle. So the goal of the contact search is to reduce the list of the possible contact to a shorter list, so I can efficiently check for the possible collision between the particles. In PhasicFlow, we use no binary search, which is a kind of cell-based contact search algorithm. And after performing the broad search or contact search step, we obtain a list of the possible contact between the particles, and we iterate through that list and find the actual contact between the particles. For example, for particle 1, we have a list of particle 1, a list of the possible contacts between particle 1 and particle 6, 4, 10, and 2. And later in the collision check or in the final stage, we check the collision or the actual collision, and we find that, okay, we have contact between particle 1 and 6, 1 and 4, and 1 and 10, not 1 and 2. Okay, this is called the contact search, and as I told you, we use no binary search in PhasicFlow for collision and contact search. The other important part of the DEM simulation is the integration of the equations of the motions, Newton's equation, second law, and Euler's second law. For many reasons, we use explicit integration instead of implicit integration. By explicit integration, I mean that we use the current position and velocity and other properties of the particle and calculate the contact force of the contact force and contact torque between the particles based on the current variables, and then integrate the equations one step in time to obtain the next velocity and position. This is called explicit integration. And to avoid instabilities, the time step of integration should be less than a period of time. This period of time is the time that it takes to transmit a wave or a disturbance from one particle to another. If we are using linear model, this critical time step is obtained from this equation. If we are using nonlinear model, this critical time step is obtained from this equation. Looking at the different literature and from our experience, the time step that required integration, time step for integration is around 10⁻⁵ to 10⁻⁶ seconds. This is a very small value for time step, and this is a really huge challenge in the DEM simulation. For example, if the time step is 10⁻⁶, it means that for every second of the simulation, you need to perform 1 million iteration or integration over time. So this is a huge number, and it requires a lot of computation to perform each second of the DEM simulation. These values that you see here are obtained based on the reduced value of the K or Young modulus. It means that if we want to actually use the real or the actual values of the K or Young modulus of the material, we even need to use lower values of the time step in our simulation. But many simulations or articles showed that reducing the value of K or Young modulus does not affect the simulation results that much, especially when we are dealing with the granular flow and particles are flowing due to some gravity or rotation of the impeller, or due to the fluid flow that we have in the solid, gas solid or liquid solid systems. So this is the critical time step, and in the simulation, we need to use a fraction of this critical time step as the actual time step for the integration. I will talk about this a little bit in the next slide. So we need to have a fraction of the critical time step in the simulation. So this fraction depends on the integration method and the accuracy and the order of the integration method that we use in the DEM software that we have. We have a lot of integration methods in the literature, and we can group them into three categories: single step, multi-step, and predictor corrector types. In PhasicFlow, we have multi-step integrators, Adams-Bashforth second order to the fifth order, and predictor corrector type, Adams-Bashforth, Adams-Moulton third, fourth, and fifth order. Of course, by increasing the order of the integration, the accuracy of the integration also increases, but at the same time, it requires more computational resources in terms of memory and CPU. So you should somehow decide which integration method is somehow better for your DEM simulation. But I want to show you some pictures here, some graphs here that somehow guides you through selecting the right integration method for your DEM simulation. You see here two graphs. The first graph is related to the multi-step integration method, and the second graph is related to the predictor corrector types. The horizontal axis is the time step resolution. The time step resolution is the ratio between the collision time and the time step that we use in the DEM simulation. And the vertical axis shows the average relative deviation or average relative error in the integration of the equations of the motion in the DEM simulation. And we set a threshold here, 1% average deviation. And if the integration method provides an error less than this value, it could be an accepted integration method for our DEM simulations. You can use other threshold values here, but here we just used 1% error. As you see here, for the Adams-Bashforth family, as we increase the order of the integration, the required time step resolution is reduced. For example, for the second and third order, the required time step resolution, the resolution in which the error falls below 1% is around 20. But for the fourth and fifth order, it is around 10 or 9. And for the predictor corrector, the situation is a bit better. For the lower orders, we have some values around 15, and for higher orders, we have values around 7 or 8. Why this value is important? Because the time step that we use in the DEM simulation should be equal or less than this value, 1 over alpha, if alpha is the time step resolution, times delta t critical or critical time step. It means that if I have a lower value of the time step resolution, I can choose a larger time step in the simulation. Larger time step in the simulation means that I can perform 1 second of the simulation with fewer number of the iterations. It means that faster simulation. Okay, this is all that I wanted to talk about the backgrounds of the DEM. Of course, I didn't cover many aspects. If you are interested and you want to get more details, you can refer to the to chapter 2 and 3 of the book to read and learn more about the backgrounds of the DEM.
So, Hamid, maybe I can ask 2 questions here. So the first thing, and thank you very much. That sounds quite nice and scientific. But the first question, or my first question, is that can we find this information somewhere documented? I think the answer is, of course, in the book. So probably you have them in much more detail already provided in the book. Am I right?
Yes, all of the information can be found on the book.
Okay, and the second question, which is more on the lazy side, so is there any of these integration schemes or any rules of thumbs that you can tell us that, okay, this is the one that if you don't want to read through the book, which I recommend you to do it, to do the things properly, but just consider that you don't want to go through that much details. So which one these integration methods and what rough time steps might be a good starting point for a simulation?
Okay.
For example, when we look into against CFD, I always give examples from the CFD side. When we want to start with the turbulence, usually we say K epsilon is like a turbulence model which works almost everywhere, but it's not that accurate. So if you want to make something work for the first time with the turbulence, K epsilon might be the starting point, but it should definitely not be the end point. So can you give us also such recommendations here?
Yes, for the integration method, I usually use Adams-Bashforth's fourth order, AB4. For the time step, if the particle size is in the range of 1 millimeter to somehow 2 millimeters, I usually use a 10 powered minus 5. If I am I'm doing simulation with the larger particles, I should rethink about the increasing the time step, because with increasing the size of the particle, I'm allowed to use larger time steps. As you see here, for example, in this equation, the critical time step is directly related to the size of the particle, or it is also directly related to the mass of the particle, which is directly again related to the size of the particle. And for smaller particles, like in range of micrometers, 100 to 700 micrometers or less, I usually use 10 power minus 6 or something like that.
Great. Thank you very much.
You're welcome. Okay, let's get back to the software and the simulation. Let's open the Okay, today I want to talk about screw conveyor and how we can perform this simulation using PhasicFlow. Here is a picture of the simulation that you see here. We have a complex geometry. Of course, we didn't use built-in tools of the PhasicFlow to create this geometry. We use a CAD application to create the 3D model, and then exported the 3D model in STL format, and then PhasicFlow can read the STL format or STL file and load the geometry for you. The internal diameter of the shell is 20 centimeter. The length of the shell is 1 meter. As you see here, the screw is a variable pitch screw, and the rotation speed of the screw is 30 RPM. We have two types or two sizes of the particles, 10 millimeter and 9 millimeter. The density is 2,300 kilogram per cubic meter. The friction coefficient is 0.3. The rolling friction is 0.2. The restitution coefficient is 0.8. Young modulus is 1 megapascal, and shear modulus is 0.8 megapascal. I want to insert particles at the top of the feeder. This is the feeder. The rate of the insertion is 2,800 particles per second, and the location, as I told you, is above the feeder. And I want to have a mixture of the 10 millimeter and 9 millimeter particle. For each 10 millimeter particle, for every 5-10 millimeter particle, I insert 3 small or 9 millimeter particle. The simulation is going to be done for 20 seconds. The delta T for the simulation is 2 times 10 minus 5 seconds. As you see here, since the size of the particle is large, we are allowed to use larger time steps in the simulation. And again, the integration method is Adam's batch force. This simulation that we are going to cover in this session is from the standard tutorials of the PhasicFlow screw conveyor, as you see here. Detailed information are given here. You can read these instructions to learn about how you can perform this simulation. But I try to cover some parts that I think that are important for this class. Let me just find the simulation case setup here.
So meanwhile, finally, we have also a question in the chat. So what's the title of the book? Can you please repeat the title of the book?
Title of the book?
Yes, please.
Yes, sure. Okay. Coupled CFD-DEM modeling, formulation, implementation, and application to multi-phase flows. Let me just copy the, you're welcome. PhasicFlow version 1, tutorials, spheregram flow, and screw conveyor. Just copy it and paste it where you want to perform the simulation. Okay. Again, we have case setup folder, settings folder, and in addition to that, we have another folder, STL. From name, it's clear that it contains the STL files for the geometry. I have 2 STL files, of course, 2 sets. One is the coarse one with larger triangles on the surface, and the other is the fine one. I think that I am using the coarse one in the simulation to somehow accelerate the simulation. Okay, let's start with the geometry creation, because I think that it somehow is the most important part of the today's simulation. For the geometry creation, we need to open the geometry dict. The motion model is rotating axis. Of course, the screw is rotating, but the shell is fixed. For defining the rotation axis or rotating axis, I need to provide the information for the axis of the rotation speed, and the time span of the rotation. For example, if you don't want to have the rotation started from the beginning of the simulation, you can define a kind of start time and end time in the simulation. If you do not provide these 2 parameters here, then the start time would be 0. It means that from the beginning of the simulation, and the end time would be infinity. It means that until the end of the simulation. So you can adjust these parameters based on your need. In the surface part, as I told you, I have 2 STL files. One is for the helix, and the other is for the shell. Since the helix is going to rotate and the shell is going to be fixed, I must have 2 different surfaces, because I want to have the first surface, helix, to be rotating, and the second surface, which is the shell, to be stationary. The type is the STL val, and the file is the name of the is the name of the STL file that I provided here in this folder. Let me just show it again. Screw.stl. I should assign a property to it. Prop1 is the name of the property that I'm going to assign it to this valve. And of course, rotational motion component name, which is rot axis, or whatever name that you want. You can set it here. For the shell, the same settings, but the only exception is the motion, since I want to have the shell stationary. I set the motion component to none. None means stationary or not moving. So this is all that we need to provide to define the geometry and the motion model of the geometry. After this, I open a new terminal. The command is geometry PhasicFlow, and you should always see the finished successfully at the end. If you see that, it means that everything has been done correctly.
So Hamid, two questions. One is from the chat. So I would like to ask if it's more convenient to use .stl file in ASCII or binary format.
Oh, sorry, that's a good question. At the moment, PhasicFlow only reads the ASCII format. But from computational point of view, there's no difference, because the STL that we are providing is not that much heavy and complex. And reading the STL and writing it or converting it into something that is comprehensible for PhasicFlow is a very lightweight operation in PhasicFlow. So don't worry, just save the file in ASCII format and then use it in your simulation.
In case that you have an STL and it's not in ASCII format, there are multiple ways to convert it to an ASCII format. So multiple tools. Of course, there are online tools, but you can go for something like Blender. Blender is a very nice free tool that you can also use for doing that. I think it's also possible to do it through ParaView, so you can also export it from ParaView in ASCII.
Exactly.
I'm not 100% sure, but I think it's possible. And yeah, so thank you very much, Hamid. Now I have also another question. Is there any limitation regarding the complexity and the size of the STL that we are using?
Yeah, that's a really good question. Of course, there are limitations, because if we increase the resolution or the number of the triangles on the surface, at the same time, we are increasing the computational time of the collision between the particles and the surface. So be reasonable and try to stick to some triangle resolution that somehow represent the actual geometry accurately, but the resolution is not that high that we cannot perform DEM simulation in a reasonable time. For example, in this simulation, let me just check. For this complex geometry that you saw here, yeah, I'm trying to remember what these values are. Okay, around, let me just check the other parts. Sorry, it's in binary format, so I just don't remember the number of triangles, but around 6,000 triangles are used in this simulation.
Yeah, from the numbers which are also in here, that looks like 6,000. So basically, as a general recommendation, as always, you have to go for this compromise between the accuracy and the speed. So of course, you want it to be as accurate as possible, but on the other hand, you have to have an eye on the speed that you can do a simulation in reasonable time. So as Hamid mentioned, make it as detailed as possible, but not too detailed. So if there are small gaps in there, if there are small details in there, that does not really change the
Just
phenomena
forget.
that you study. Just simply forget it and move forward.
Yeah, and if I was going to perform the simulation for an article for this screw conveyor, I would use the course STL here. But since I wanted to somehow create nice animation out of this simulation, I used the fine resolution for the surfaces. Just don't worry about it. Go for the coarser STL files. You will get almost the same results. Okay, the next step is particle creation. In this simulation, at the beginning of the simulation, we don't have any particles, but we are required to provide the files for the particles. For example, the position of the particles, velocity of particles, even though it is an empty simulation at the beginning of the simulation. How we can do that? It's really easy. Just we can go to the particles dict. And as you see here, again, for positioning particle, we just use empty as the method. It means that we have no particle at the beginning of the simulation. And we also need to provide the default values for the velocity, acceleration, rotational velocity, and shape name. So that's easy. And we execute the command particles PhasicFlow. And let's have a look inside the 0 folder. As you see, P structure contains the position of the particles, velocity of particles. As you see here, there's no particle or no information in this file, but we should provide it. Okay, up to here, we created an empty simulation. We created the geometry with its motion model. Now I want to define the physical properties, define the particles, the interaction parameters between the particles and particle walls, and also define or create a mechanism to insert particles during the simulation. As you saw in the animation, the particles are being inserted into the simulation during the simulation. So all of these are possible through this case setup folder that you see here. Let's start with defining the shapes and then interaction, and at the end, particle insertion. The shapes contains the shapes file contains all of the shape names. Here I have two sizes. The name of the particles are, for example, here, sphere 1 and sphere 2. The diameters is 10 millimeters for sphere 1 and 9 millimeter for sphere 2. The material property name for both particles is prop1 and prop1. That's all. If you want to have one size of the particle, you just need to have one name here, one diameter, and one name again here. And if you want to have more than 2 or 3 or 5, you can do that easily in this file. The next file is the interaction. This is something that is new for us. For the interaction, I need to define all the materials that are in the simulation. We have one material. You can define more than one material. You can find some tutorials in the PhasicFlow folder or in the PhasicFlow repository that has more than one material. Okay, the name of the material is prop1, exactly the name that I used here for the particles, and the density is 2,300. This parameter is always this sorted contact list. I don't want to talk about it at the moment, but the important thing here is the contact force model that is defined here. The contact force model is nonlinear contact force, and the friction model is non-limited. Again, I didn't cover the limited and non-limited friction model. If you are interested in learning about these two types of the friction models, you can refer to the book. Then the rolling friction is the normal, the one that I introduced in the slides. As I told you, when we are using nonlinear contact force, we are required to define the Young modulus, shear modulus, Poisson's ratio, coefficient of normal restitution, dynamic friction value, and rolling friction value. These are the parameters that we need to define for the nonlinear contact force. That's all. By providing these, we have provided everything for the calculations. For the particle insertion, if I want to have particle insertion during the simulation, I just need to provide this file in the under the case setup folder. I can have more than one region for particle insertion. For example, if you have two regions from which particles are being inserted, you can define two dictionaries here. The name of dictionary is feeder. You can choose whatever name that you want, but the content is important. Here, I only have one insertion region. So you see one dictionary here, feeder. Okay, the rate is referring to the rate of the insertion, 2,800 particles per second. The time control defines how I want to control the insertion sequence in the simulation. We have two options, simulation time and time step. When I choose it, set it to simulation time, it means that everything that I am defining for start time, end time, and insertion interval is in seconds. If it is time step, then start time, end time, and insertion interval are based on the time step or in iteration. Okay, here I'm defining that, okay, the in particular insertion starts at 0 or at the beginning of the simulation and ends at 100 seconds. Each insertion occurs every 0.04 seconds. And I also need to define somehow the region from which the particles are going to be inserted into the simulation. We have three types, I guess, here: box, sphere, and cylinder. Let's check the options. If we get the list of the options here. Box. Okay, no. This part is not the type of the banana part. The banana method does not work with the banana method. Okay, as far as I remember, box, sphere, and cylinder are the options that we have here. For the box, I need to provide the coordinate points of the box. These coordinates that you see here are the coordinates that defines a box on the top of the feeder. And also, I need to provide the initial velocity or any other parameters or any other variables for the particles. But here, the initial velocity is the most important part. I need to provide the initial velocity of the particles. If I do not set the initial velocity would be 0. But here, as you see, I set the initial velocity of the particles in the y direction, but in the negative direction again. It means that, okay, when the particle is being inserted, the initial velocity of that particle is in the negative direction. The mixture is defined here, sphere 1 and sphere 2. These are the names of the particles that we chose here. And this is the number composition of the mixture. It means that after inserting every 5 sphere 1, insert 3 sphere 2 into the simulation, and again repeat this sequence until the end of the insertion period. Okay, these are the settings that we should provide for defining the insertion of the particles into the simulation. The other file that I did not cover in the last session is settings dict. It's simple. The run name is not that important, but it's nice to have a proper name for the run name. The DT is the time step for the integration. This is very important. And the start time and end time are set here. Start time here is 0 and end time is 20. But for example, suppose that you have performed the simulation up to 20 seconds and you want to continue the simulator. It stopped and later you want to continue the simulation from time 20 seconds. Then it's fairly straightforward. You just need to set the start time to 20 and end time to something that you want. Save interval refers to the intervals between each moment of the results that are being saved on the disk. So this is something that you set for as you want. Time precision is the number of the decimal points that you use for representing time in the simulation. G is the gravitational acceleration. As you see here, it is a vector and the value is 9.8 in the negative y direction. The right format could be ASCII or binary. Here I chose binary because the size of the data is large, and with ASCII it takes much longer time to save data on the disk. Integration method is set here around /force 4. As you see here, I also have another options. Integration history is set to off. It means that everything and every variable that is related to the integration method should not be saved on the disk. This is something that we choose and we have for reducing the size of the simulation files on the disk. Time report and timers report and timers report interval are not very important, but here the important one also are include objects and exclude objects. By default, PhasicFlow saves the results or saves the particle fields on the disk. For example, for velocity, rotational velocity, and the position of the particles, identification number of the particles, and so on. And it also misses some objects and some variables for the particles during the results being saved on the disk. If you want to change this behavior, you just need to add those parameters or those variables in this list. For example, by default, PhasicFlow does not save the diameter of the particles on the disk. But here I want to have the diameter of the particles. That's why I add the diameter here to somehow include the diameter as the save list. And if, for example, if I want to reduce the size of the files on the disk and somehow avoid saving unnecessary data on the disk, you just need to list the name of the variables in this double parentheses. So during the save operation, these parameters and these variables are excluded from the list. Okay. Up to here, I think I covered everything, and we are ready to perform the actual simulation. The solver is spheregram flow, and as you see here, at the beginning, particle insertion occurs. Particle insertion from feeder. This is the number of the particles and the number of particles that are being inserted from this region. And again, another insertion of the particle occurs, and this happens during the simulation. Okay, the simulation takes time, and again, if you want to see.
So, I mean, meanwhile, maybe we can answer a few questions. the simulation is running, or at least the first part of the simulation is running. So we have a question here. Do you have some hint for good tool for complex geometry creation in PhasicFlow like Blender or some CAD tool? That's something that I can also answer. Basically, there are a couple of nice tools out there. You already mentioned Blender is definitely an option for do that. But you can also use tools like FreeCAD, which is an open source free CAD tool. You can also use tools like Saloom. So I also really like that. Saloom does not just create the geometry, you can also do the meshes for the CFD simulations with it. And of course, there are many other also CAD tools out there like SolidWorks, CATIA, so you can use any of them. So as far as the tool that you're using can create STL for you, then you're good to go. Then comes the next question. Can PhasicFlow handle heat transfer to the particles? If so, is it possible to set some of the thermophysical properties such as viscosity, specific heat of the particles as a function of temperature?
Yeah, that's a really good question. We are going to add the thermal calculations for DEM and of course CFD-DEM part of the PhasicFlow. Of course, when we are designing this part, maybe in the next year, we think about this option, a constant property and a kind of property is variable with temperature, that is function of the temperature. But at the moment, the short answer is that we don't have any heat transfer in PhasicFlow and PhasicFlow Plus.
Good, thank you. And the next question is that what is the option active insertion? Can you please explain it again?
Okay. Yes, I didn't explain it. Active could be yes or no. If it is yes, it means that the insertion is active during the simulation. And if it is no, nothing happens. No particle is being inserted into the simulation. This is some option that enables you to somehow turn on or turn off the insertion based on your need. And if, of course, if you want to remove or if you don't want to have a particle insertion, the other way is to delete. Where is it? Yeah, delete this file from here. If the code does not find this file here, it means that there is no particle insertion during the simulation.
Good. Thank you very much. Now there is also another question. What's the difference between PhasicFlow and PhasicFlow Plus? Basically, PhasicFlow is our DEM code, and PhasicFlow Plus is the coupling between the DEM code, PhasicFlow, and OpenFOAM. So with PhasicFlow Plus, we can do CFD-DEM simulations.
Yes, thank you for nice explanation. Okay, it takes time to perform 20 seconds of the simulation, but I did the simulation before. Let me just find it here. Okay, I performed simulation up to time 8. Suppose that we have finished the simulation and we want to visualize the results in ParaView. Sorry. For doing that, we use pflow to VTK. As I told you, it has some options. These are the command lines options that we have for the important here is minus binary and maybe fields. If you want to choose among the fields that you see in each folder, you may want to choose a subset of the fields to be converted to VTK format. The time span, maybe you want to convert the results for a certain period of time, not all of the time folders. And another important and maybe useful option here is separate surfaces. It means that if you created your geometry out of two different surfaces, you can have the results in the VTK format in separate files. Then you will be able to somehow load them separately in the ParaView, and this will enable you to perform a kind of operation on ParaView, in ParaView, independent operation on these surfaces in ParaView. This is something that that is useful in some cases. So let's start our conversion, pflow to VTK minus separate spaces minus binary, and I want to have fields, for example, diameter, velocity, and ID. That's it. Any questions? Because it takes like 1 or 2 minutes to finish.
There are no questions in the chat at the moment. We have around 9 more minutes, so to the end of the session.
Okay. You just need to wait for 1 minute, I think.
Maybe I have a question. So do we have also any option, again, for those of you who are familiar with OpenFOAM, you know there is the option .foam files that you can load them in ParaView. Is there such an option also in PhasicFlow? Can we also load it like that in ParaView, or we have to convert it to VTK?
At the moment, no. I think that this could be a very cool option, of course, because converting from the OpenFOAM format, PhasicFlow format to VTK format takes time, and sometimes we don't want to have this. I have think about it before, but I have no solutions at the moment for that. Maybe later we write a kind of plugin for ParaView, then you use that plugin to directly read the PhasicFlow results into the ParaView, not converting it into the ParaView and then visualizing the results.
Mm-hmm. So that's basically something which needs to come from ParaView side.
Yeah, and ParaView, since there are many users of the OpenFOAM around the world, ParaView has this plugin as the standard plugin in the ParaView. So when you load that foam.foam in ParaView, ParaView knows that this is an OpenFOAM simulation, then calls the OpenFOAM reader in it to read the simulation results for you.
Mm-hmm. Great, thank you.
ParaView, you're welcome. Okay, in the VTK format, I have 2 files for the surfaces. One is for helix, and one is for the shell, and also 1 file for particles. I load them. Okay. Since I have 2 files here, or 2 databases here for the surfaces, I can, for example, independently change the opacity of the shell, so somehow you can see inside the shell. Let me just go. I don't want to visualize the particles using actual spheres. I just visualize them using their center points. I just forgot to add another thing here. Not a time. Okay, that's better now. If you remember, when we were setting the motion model, the rotation the start time of the rotation was set to 1. So as you see here, up to time 1, we don't see any rotation, and after that, we see that the rotation starts.
Good. Hamid, we have another question in the chat.
Okay, as I told you, since this is very heavy, it is very slow to visualize. Okay, go ahead.
I observed that the insertion was done using particles per second, but when you don't have the information of particles per second and only have real flow rate in kilogram per second at the phase, then how can it be handled here?
It's really easy. Just calculate the mass of one particle, and then by dividing the actual flow rate of the solid by the mass of the particle, you will get the number of the particles per second.
Great, thank you very much.
I mean that you just have this option to define the number of the particles per second in the current version of the PhasicFlow. But if you have trouble to converting the kilogram per second into number of particles per second, it's really straightforward. Just divide that value by the mass of one particle, then it will be converted to the number of the particles per second.
Thanks.
Okay, you're welcome.
We have,
as you see here, this is the simulation condition up to time 8. Okay, go ahead.
Is it possible to do insertion as an intersection of objects?
What do you mean by intersection of objects?
Probably it means that we have two insertion planes which are somehow intersecting with each other. To my point of view,
yes, I think it's possible,
but I don't recommend it, because it might be that two particles get inserted at the same location or with a very big overlap, and then basically a very huge force will be calculated and they will be shooted out. Please, Hamid, correct me if I'm wrong.
Bahram, I cannot hear you. Sorry.
Oh, can you hear me now?
Yes.
Okay, great. What I mentioned is that I think it's possible that you have two insertion planes that are intersecting with each other, but I don't think it's a very good idea to do that, because it might be that they are inserting particles at almost the same location or with very big overlaps, and that ends up in very huge forces, and during the integration it will shoot the particles out with a very high acceleration and speed. And it leads to instability and divergence of the simulation. But Hamid, yes, please correct me.
No, that's right. That's completely right. But one important property of the insertion mechanism here is that when we are inserting new particles into the simulation, it also checks for the collision between the new particles and the previous particles in the simulation. So it is 100 guarantee that you don't see any collisions between the newly inserted particles and the previous particles in the simulation. But between two insertion regions, we don't have this collision check at the same time. So that the explanation that Bahram gave is 100% correct.
Great. Thank you very much. And we have one more minute.
Okay, thank you. And okay, if you have any questions regarding this simulation or other things that are related to DEM or PhasicFlow or PhasicFlow Plus, we can be in contact on LinkedIn or through the comments in the YouTube channel. Again, thank you everybody for being with us. I hope this session was helpful for you, and see you next Tuesday. Bye.
Also, thanks from my side. Thanks for being with us, and see you next week. Bye.